Welcome back to College Algebra for Business. This is section 7.1, but it's going to be 7.1b. We're going to be doing some more work with combining functions. Now let's talk about something that I did not review in the previous video for this section, but I would like to go ahead and review it now, because if you have something like f of x equals 2x, you can evaluate that function for various values of x. Let's evaluate it for the value of x that is -3. So wherever there's an x, I'm going to put in a -3, and that will give me the function of -3 equals -6. What if you substitute something a little more complicated in here? What if instead of a -3, we substitute, I don't know, x plus 2? Can we do that? Well, whatever is inside the parentheses on the left-hand side, we are going to put inside the parentheses I'm putting in, because that's where my x goes. 2 times x, well, instead of x, I'm putting in x plus 2, because that's what's over here. So what I have here is the function of x plus 2 is equal to 2x plus 4. But wait a minute, that x plus 2 looks an awful lot like a function itself. In fact, I'm going to go ahead and call it a function. I'm going to call it the function g of x, because I can put various values of x in there, and the function will return some other number. So if I put in 10 for x, this function will return 12. So the function g of 10 equals 12. But let's take a look at this. I took this x plus 2 earlier and put it inside the function of f right here. So really what I did over here was this. I took the function f of the function g of x. So I had my function f equals 2x, and wherever that x was, I put in my function of g. But we have already determined that this is actually equal to 2x plus 4. Now we can plug 10 into this composite function. So 2 times, that's where our x will go, plus 4, and I will insert 10 in the parentheses in place of the x. So the function f of g of 10 equals 24. And we can write it that way. Now, take a look though. We could have just taken 10, plugged it into g, found the answer, and then put that into our function f. So let's do that and take a look at what happens. So the function f of x is equal to 2 times x, but we're going to put the value that we got when we plugged 10 into g, take that 12 that we received, and put it in for x in our f of x. And what do we get? We get 24. So this two-step process gave us the same answer that we got with our composite function. And all we had to do was plug in a number once, and it returned the value of 24. Now, to a mathematician, this composite function is more efficient. Oh, one other thing. Why use just one notation when you can use two different types of notation for the same concept? The function f of g of x, which in our case equals 2x plus 4. So all of this work was to give you an idea of how a composite function is formed. All right, let's compose some functions. Let's start with the function c of n of x. So as I'm writing this, I'm going to write 3. I'm going to write my c function first, And everywhere there's an x, I'm going to leave room for the entire function of n. And that x is squared in my c function of x. And then I add 2. Now, inside those parentheses, I'm going to put n of x, which is equivalent to, or the formula for that function is the square root of x minus 1. I now have a composite function composed of c and n. Let's make it a little bit easier to understand. I am squaring a square root, so that just becomes whatever the radicand is. Okay, and then I have to add the 2. Now I can distribute the 3, and my final answer is the function c of n of x is equal to 3x minus 1. Let me move this up here, and we'll work on another one. This time, I'm looking at n of c of x, the function n of c of x. So first I'm going to write my function of n. I'm going to leave room to insert the function of c where my x is in the function n of x. And now I'm going to insert my function of c, 3x squared plus 2. And let's see if this can be made any simpler. Let's see, I have the square root of, don't really need those parentheses underneath here, and that will give me 2 minus 1 will give me a positive 1. But 3x squared plus 1 is not a perfect square. There are no squares I can pull out of there. If these were multiplied, if it were 3x squared times 1, I could take the square root of that x squared, but because I have a binomial, I cannot do that here. I'm done. So let's take a look now at the function c of p of, wait a minute, p is a function of a, and c is a function of x. What variable should I put here? This very case is a good example of why sometimes it's better to use all those parentheses. So I can write c of p of a. So a is the innermost variable. And what this is going to look like is I have 3, I have an x that is squared plus 2. That's my function c of x. I'm going to put inside this function where the variable is the function p of a. And the function p of a is right up here. It's 3a. Now I'm just using my order of operations and moving down through here to simplify this as much as I can. So the function c of p of a equals 27a squared plus 2. Now what if a is 2? What would that be? That would be c of p of 2. And I believe that is equal to 110. Now we could have taken that 2 and put it into the function p of a, gotten that value, and then put that in to our function c of x. We would have put whatever the value we got here was in for x. But if we wanted to change variables, we would have to put the new variable in for a, return that function, and then put that in here. Or we could run each of those variables of interest right into this simpler equation here. That simpler expression of the compound function. Does this have any type of real-world application? You betcha. Marlin makes doohickeys out of aluminum. Now, don't you love these real-world applications? Now, Marlin has been doing this for years, and so he has determined that if he measures his aluminum that he purchases in kilograms, then this formula here will tell him how many doohickeys he can make out of those kilograms of aluminum. So we can actually call this the function d of a, kind of standing for how many doohickeys you can get out of the aluminum. And then he's also figured out that for every doohickey, which he sells for $1.50, he's going to make some money, right? But to participate in this festival, he has to pay $75 for a booth. So his profit in doohickeys, for selling his doohickeys, can be expressed with that function. Now, what does that tell us? What profit is he going to make? Well, if he has 10 kilograms of aluminum, we could put that 10 kilograms in here, figure out what this value for d of 10 would be, and then put that value into the next function. But what if he wants to think, well, maybe I want to buy 15 kilograms, so I have to put that in here, figure it out, put it back down in here. Why don't we compose the function for him so he doesn't have to do that every time? So without the fancy colors this time, let's do this. So I want the function p of everything else. So I start with my function p, and wherever I have a variable in there, I leave room for the function I'm going to put in there. And then I finish writing minus 75 because I need 1.5 times my variable minus 75. 1.5 times my variable minus 75. And what's the variable I'm going to put in? The function for doohickeys, d of a. So I have to write a little smaller here. 50a minus 175. And there we have it. There's the formula. We can make this a little bit simpler. And so if we distribute that 1.50 and then combine like terms, here's the function that we get. And this is the function for the profit that Marlon is going to make. And it is all based on the amount of aluminum that he buys. So really, this is the profit as a function of A. Although originally we were thinking of the profit as being a function of the number of doohickeys that Marlon produces, it's actually a function of the aluminum that he buys to build the doohickeys, which he then sells for a profit. So if Marlon buys 10 kilograms of aluminum, he should be able to make a profit of $412.50. Okay, let's get a little artsy here. Let's consider this green graph to be the function f of x. And the yellow graph will be the function g of x. So let's do some addition and subtraction of these also. Let's find f plus g of x for x equals 2. Okay, so remember that that is equal to f of x plus g of x, or f of 2 plus g of 2. So what we need to do is look at this graph and try to determine where f of 2 is. So let's see, here's 2, and it looks like we are at 2. So the function f of 2 is 2. And then we add to that the function g of 2. So where are we at 2 when we're looking at the function of g? We are down here at -1. So we're going to add a -1. So 2 minus 1 is 1. Therefore, the function f plus g of 2 is 1. We can also subtract. So let's take g minus f of 3. 3 is 1, 2, 3 right here. We're going to find g first. Oh, well, we're right there. It's 0. So g of 3 is 0. We're going to subtract from that f of 3, So f is at the value 3 at 3. So I have 0 minus 3. If we subtract the function f from the function g at 3, we get the value negative 3. Adding and subtracting on a two-dimensional graph kind of makes sense. It's harder to visualize something like multiplying f times g at 4. So let's see. At 4, 1, 2, 3, 4, the f value is 4. And then we're going to multiply that by the value of the function of g at 4. 1, 2, 3, 4. 1, 2, 3. So 4 times 3 is 12. So you can read all of that from a graph. What about composition of functions? To make this a little bit clearer, I think I'm going to use the nested parentheses notation for this. But both of these things that I've written here are equivalent function notations. And let's evaluate these composite functions at a value of 2. Okay, so we will take the inner one first. So the function g of 2 will give us what? 1, 2. Function g of 2 is negative 1. So now we need the function f of negative 1. And what will that give us? So we find the function g of 2 that returns a negative 1. Then we take that negative 1 and we go to negative 1 on our graph and read the value of f of x. And that value is 1. So that's our final answer, 1. The function f of g of 2 is equal to 1. Let's do it again for a different value. Let's try f of g of 3. So g of 3, what would that be? Let's take a look. 1, 2, 3, that's 0. So 0. And f of 0 is, 0. So in this case, our function f of g of 3 is 0. Let's try g of f. Let's try g of f at 2 and see if it makes any difference. Okay, and instead of writing it that way, I will write it nested. So here was my first example, here was my second example, here's my third example. G of f of 2. What would that be equal to? I've run out of room there. Okay, so I'm doing f first. So f of 2 gives me what? 1, 2, 1, 2 gives me 2. And g of 2 gives me what? 1, 2 gives me a negative 1. So g of f of 2 equals negative 1. Now it's time to discuss decomposition of functions. Before we jump into decomposition of functions, let's just talk about separating functions. All right, here is an addition of two functions, g and f. This is already combined, it's already added. What if you know that g of x equals 1/2 x cubed minus 3? What does f of x equal? Well, the only thing left is f of x must equal 2x, because if you add those two functions, you get our original function. So let's look at the function f divided by the function g of x. And that function is 1 over 3x. we know, or I'm telling you, that the function g of x is equal to 3x squared. What is the function f of x? Ooh, this one's a little bit harder to figure out. So let's rewrite the left-hand side, because there are different ways we can write this function notation. If you remember back from our addition and subtraction, multiplication and division, what I wrote on the left-hand side of the equals sign in my original expression there of the function can be rewritten as the function of x over g of x, which is equal to 1 over 3x. However, we know that g of x equals 3x squared. So we can substitute that into our ratio on the left-hand side. G of x is equal to 3x squared. Let's see, and we're solving for f of x, right? So what happens if we multiply both sides by 3x squared? 3x squared. F of x equals x. Does that check? Let's see. F of x over g of x. We said that f of x equals x, and we know that g of x equals 3x squared. And if we reduce that, yeah, we get 1 over 3x. It checks. Here is our answer. All right, now it's time to talk decomposition. So let's look at this example. The function f of g of x equals the absolute value of the binomial x squared plus 1, and then added to that absolute value is 9. We know, or I'm telling you, that the function g of x equals x squared plus 1. So what is the function f of x? We're trying to decompose this. We have one of the functions. We need to find the other function. Well, for this one, let's revert to color. Now you can clearly see in this one at least where g of x is. So f of x must be everything we see there except where g of x is. That's where our variable is in f of x. So here's one that's a little bit trickier. The function n of c of x equals the square root of 9x squared plus 9, and then subtract 1 from the radical. And our function c of x equals 3x. Where is 3x in this? I don't see 3x. I do see an x squared here. And I see 9, which, is the square of 3. So what if I rewrote what's under the radical here instead of 9x squared? What if I rewrote it as 3x squared? But the squared isn't part of my c of x. So let's leave it yellow, because I have found this 3x that I was looking for. If I make it red, does it become more apparent that that's what I was looking for? So now I know that this composite function took 3x and squared it to get the original composite function. For n of x must be the square root of x squared plus 9 minus 1. And this concludes our series of videos on combining functions. I'll see you in class.